Hello and welcome to this Chapel tutorial and to our open source community. We'll have 3 speakers in this tutorial today: Jade, I'm Michael, and Daniel. Here's an outline for this Chapel tutorial. We're going to start with some information about how the Chapel programming language is helping its users. Then we'll look at the heat diffusion problem and how to implement it in Chapel. We'll continue by looking at how to make it parallel, including how to run on GPUs or multiple nodes. Here I've listed the Chapel language features that we'll cover in each section. If you're looking back at this video or looking at the slides offline, hopefully those will help you go to the section that you're interested in. What is Chapel? It's a programming language for efficient and accessible parallel computing. Parallel computing is important because it allows programs to run much faster. The trouble is, most languages are designed for sequential computing. Let's look at an analogy to understand the difference between sequential and parallel. Imagine you want to grow enough wheat to make a loaf of bread. You could grow the wheat sequentially by planting one seed and waiting for it to grow before planting the next seed, as with this picture on the left. It's called serial or sequential. It would take quite a long time to grow enough wheat to make a loaf of bread with this approach. Or you could grow the wheat in parallel, as in the picture on the right, where the wheat plants are growing simultaneously or at the same time. That would allow you to get a lot more wheat more quickly, and it's a more efficient use of resources. Chapel is helpful for parallel computing because it's designed for easier expression of parallel programs. This allows Chapel users to write parallel programs that work across a whole spectrum of parallel hardware, from laptops, workstations, and GPUs to compute clusters and supercomputers. As a result, Chapel is easier to learn than competing technologies for parallel computing. One group found that new students could contribute 8 times faster, getting up to speed and contributing a useful component to a simulation. In 2 other studies, researchers found that Chapel was more productive than Python for writing parallel scientific applications. It's important for a parallel programming tool to enable performance, since the chief reason for doing parallel computing is to achieve performance, and Chapel can enable performance from laptops to supercomputers. We've seen benchmarks written in Chapel meet or beat performance of benchmarks written in other languages, and applications written in Chapel have been able to attain new levels of performance that were not seen in those contexts before, and this can happen both on supercomputers as well as on desktops or workstations. Chapel is helping users today with real-world simulation and analysis tasks. It's ready for use. Here are some references. If you look at the slides offline, you can study these links if you want to see the evidence for the claims I was just making. Now I'll turn it over to Daniel to talk about the heat diffusion problem.
The problem we'll be looking at today is modeling heat diffusion. The crux of this problem is figuring out how heat propagates through a material, like this rod in the bottom right corner of the screen. As you can see in the photo, at the center the rod is almost white hot. However, as you get closer to the edges, it's turning red and then black, and even though it's still hot, there's no more glow. So the way that the heat propagates through a material is actually determined by the laws of physics and modeled by a differential equation. And to figure out how heat propagates through this rod, we'd have to find some kind of solution to this differential equation. There are many ways to do this, but what we're going to do is an approach called direct simulation. In this case, we will quite literally be simulating the flow of heat from the center of the rod, where it's really hot, outwards towards the edges. Of course, our approach will work for general heat distributions through a material, but our example will be very similar to the one in the picture. Direct simulation is a straightforward approach, but the techniques similar to this approach are used in production-grade Chapel software such as CHAMPS, which is a 3D multiphysics simulation. Now let's take a closer look at the differential equation. I should say that you need no familiarity with differential equations to be able to follow this chapel tutorial. If you do know differential equations, then great, but the details of this are not super important to understand the material. This differential equation governs how heat propagates from hotter regions of a material towards colder ones. In the example on the slide, right, at time equals 0, the center of the rod is very hot, while the edges are lukewarm. However, as time advances and we get to a certain point in time called t, the heat has moved from the extra hot region towards the colder regions in the rod. As a result, we have a more diffuse heat gradient. The way that we'll approximate this differential equation will be by using a discrete form. A discrete form looks something like this, and it breaks up the rod into little pieces, each of which has a particular temperature. So in this case, I've split it into some squares, and each square has a particular temperature value modeled by its color, or represented by its color. Then we'll approximate the heat as it moves between squares in fixed size time steps, all the way until a certain point. In this case, the number of steps we've approximated is denoted by the big N. We'll do this by effectively applying this equation, which is a little bit noisy, but on the whole not too complicated, to the current time step's temperature values to produce the temperature values in the next time step. In this case, the important property of this equation is that the temperature of a particular cell in the next time step only depends on its temperature in the current time step as well as the temperatures of its neighbors. As a result, we can do what's called a stencil computation, in which we use a fixed region of an input array to compute the result of an output array. Of course, we'll store the next time step's temperature values in a separate array to prevent polluting the array and changing the outcome of our equation in simulation for other points. So in my photo, what I have is a visualization of the stencil equation. So the gray arrow selects 3 cells at around index I, so I, the cell whose temperature is being computed, as well as its neighbor cells I-1 and I+1, and then uses those, as well as a fixed constant alpha, to compute the temperature in the next time step at index I. In this case, we're moving from time step 0 to time step 1, but we'll do this many times. Of course, we need to compute the temperature value in the next time step for every point, so on the whole, our computation will look something like this, where we have 1 stencil arrow for each output point in the array. So now I'll show an implementation of the discrete finite algorithm in Chapel. The bulk of it is here on the right of the slide on lines 1 through 11. It might look a little bit intimidating at first, but I'm going to go through this piece of code bit by bit, starting with lines 1 and 2. So here we are doing the discrete portion of we're setting up for the discrete algorithm implementation. We take a number of points called nx, which is declared off slide, but it's just an integer variable, and creating omega, which is a domain of points numbered 0 through nx minus 1. So here the less than sign means not to include nx in the range. So as a result, we have a bunch of indices numbered 0 through nx minus 1 called omega. We also define another domain called omega hat, which does not include the point 0 and nx minus 1. The reason for this will become clear later, but it has to do with the boundaries of the array and how they fit into the stencil computation that I showed on the previous slide. Now, throughout this program, we could have actually replaced omega with 0 through nx everywhere that it occurs in the code. And we could have replaced omega hat with 1 through nx minus 1. However, in this case, it helps to name these domains, and it will become extra helpful as we move towards making this code parallel and maybe even distributed. Once we have the number of indices that we have to break up our rod into, we declare the actual array that contains the temperature values over this domain. So on line 3, we have an array u that is an array of real numbers all of which are initialized to 1.0. This array is declared over the domain omega, which means that only the indices in omega can be used to index into this array. Thus, as you can see in this bullet point, u of I is only good and valid if the index I is greater or equal to 0 and less than nx. We then also initialize the middle of u with a different temperature value so that our heat has something interesting to do, such as flow from the inside to the edges. Finally, we also create a copy of u called un to contain the values of temperature in the next time step. The result is two arrays that have the middle of them initialized to a real number 2.0, whereas all the other elements are initialized to 1.0. Then finally, we iterate and do n time steps, and for each time step, we apply our stencil algorithm. In this case, I use a for loop over omega hat to visit every index that's not at the edge of the input array and apply the equation that you see at the top of the slide. That would be lines 8 through 10. I use omega hat instead of omega to exclude boundaries. The reason for this is that, as you saw earlier, the stencil relies on neighbors that are both on the left and on the right of the current point. However, the points at the very edge of our array un do not actually have left and right neighbors respectively, because they are at the edge. So if we were to apply our stencil algorithm to every point, we would end up accessing the array out of bounds. Here's what that might look like. If I were to switch for I to iterate over omega instead of omega hat, the stencils would go out of bounds. You can see that where the gray squares of the stencil arrows pointing out or poking out from the edge of the array un, and this would be bad. In some cases, this would cause a crash, or if you disable the runtime bounds checking, this would simply cause an invalid memory access. Then, between each time step, we swap the arrays. That happens on line 7. The reason we do this is that the array u is now finished, and we've computed the temperature values at the next time step, and we're interested in the time step after that. So we should be using u as our new starting point, and then we need scratch space for the next time step's data. Since we only need one time step at a time, we can throw away the original time step and use un as our scratch space. And now I'll turn it over to Jade for our first hands-on activity.
And now we can go ahead and check out some of these examples. So the first thing that you'll want to do is open up this link and either open up the code in a code space or download the repository and use your local Chapel install. So I'm going to go ahead and follow this link. I've already got it open in my browser, and I'll go ahead and switch to that. And now we can see in our browser all the different code examples, and if I want, I can go ahead and open up my code space. I can now compile my Chapel code. So we'll compile Chapel serial, and we'll compile with -- fast. And it's successfully compiled, and I can go ahead and run it. And we can set a variety of options when we run it. So one of the things that I can do is I can set image equals true to enable image output. And when enabling image output, I want to restrict the problem size a little bit. So we can set values to something a little bit smaller. And now I can go ahead and run this and see what happens. So the program finished running, and you'll see in this folder there is now a heat.mp4 file, and I can go ahead and download this to my computer. And if I open up that file, we can now see our heat diffusion being played on the system. And I'll just drag through this real fast. As you can see, everything kind of diffuses out towards the edges and gets a little bit more blurry. So go ahead and try this out for yourself in the code space, or feel free to download this repo and try it with a local Chapel install. If you got everything working with the last activity, try this as well. We can take our previously compiled executable -01 here, and we'll go ahead and time it with various problem sizes. So we can again use those same configuration variables to change the problem sizes that we're using, and we can start with a small problem size and scale that up and see how the runtime changes. This is just another way that you can play with the configuration constants, and especially if you want to enable --image and see what it outputs. So go ahead and try this for yourself if you'd like.
Let's look at the --fast flag that we've seen on a few slides now. One of the things that --fast does is it disables runtime checks. You might not want to disable runtime checks during development because those runtime checks help us to find and diagnose bugs. But all that said, it is important to use --fast when you're measuring performance, because these runtime checks can be expensive, and because --fast will enable more compilation optimization. Let's look at an example with the heat diffusion where we've modified the for loop to go over omega instead of omega hat. This makes the array indexing to get element I-1 out of bounds. Let's see what happens if we compile this with and without --fast. First, we'll compile it with --fast. So it just ran. It ran without complaining about anything because the nature of the bug we've introduced is that it accesses undefined memory. So it doesn't necessarily crash, but it could. Let's compile it without --fast. This will enable a bunch of runtime checking. So you can see here it says that on line 20 we had an out-of-bounds array index. If we go to line 20, we can see here I-1, if this is omega and not omega hat, then I-1 is not inside of this array, or this one, these arrays over omega. So you can see with --fast, there's no particular error checking of those out-of-bounds array accesses, and if we run without --fast, we got a reasonable error message in that case. I'll turn it over to Daniel to continue with the presentation.
Thanks, Michael. Now that we've introduced this piece of code and ran some experiments with it, I want to talk a little bit more about the various language features that we used here. The first language feature is variables, and these are very much like variables in other languages such as C++ or Python. In Chapel, you declare variables using several keywords, but most notably const and var. So a const is a variable that does not change throughout execution, whereas a var is a variable that does. In this case, omega and omega hat we declared as const variables because the number of elements into which we break up our simulated rod does not change as the program executes, whereas the arrays u and un are variables because we change the numeric values stored in them as we propagate the heat through our material. There are many ways to declare a variable. In some cases, you can do this using only an initialization expression, like on lines 1 and 2. Here, we're assigning omega and omega hat a value or a range, and in this case, we don't have to specify the type ourselves. Chapel, however, is a statically typed language, so it will infer the type for us. This also happens on line 5. On the other hand, we can also specify a type, like we do on line 3. On line 3, we say that the array U is an array of real numbers over the domain omega. If you don't provide an initialization expression, but you do provide a type, then the default value for that particular type will be used. There's also some other types of variables that we don't have in this example, such as params, which represent compile time constants. The next thing we'll talk about are ranges, and I've talked about them just a little bit already, but a range is simply a sequence of integers or other numeric values. In our particular case, it's integers. So on line 1, I've declared a range that goes from 0 up to, but not including, the number nx. Ranges such as 1 through 6, which you can see in the example block on the right of the screen, represent the sequence that includes both the starting point and the ending point. So 1.6 are the numbers 1, 2, 3, 4, 5, and 6. Chapel's ranges are always expected to be written such that the left or the first value is the lower bound and the second value is the upper bound. So if you were to write 6.1, you would be asking for a range of numbers that are bigger than 6 but less than 1, of which there are none. You can also leave off boundary points for ranges, like I did with 3. And in this case, there's no upper bound and the sequence is infinite. There are some types where the number of elements is finite. You could have a range over booleans, I think, but it wouldn't make a difference, or you wouldn't have an infinite range because there's only true and false. But in the case of 3. You have the numbers 3, 4, 5, 6, 7, and so on and so forth. The less than operator, which we already used on line 1, is used to exclude one of the points on in the range. So if I were to write 1 less than 6, that would exclude the number 6, and we would only end up with numbers 1 through 5. Finally, if you did want a range that goes in reverse, you would use what's called a stride using the by keyword. And so in this case, 1.6 strided by -1 gives you the number 6, 5, 4, all the way down to 1. The next language feature is arrays, to which I've already alluded as well. Here we declared U to be an array declared over the domain omega and containing elements of type real. The general syntax is the domain of the array, D, in square brackets, followed by the type of the elements. The domain is used to represent the valid indices into that array, or indices that you can use to access elements of U. Chapel has array literals too, though we don't use them in this piece of code. You could write an array literal by surrounding a sequence of values in square brackets. So 539 is a 3-element array with the elements 5, 3, and 9. Finally, Chapel has loops, which are similar to those in Python. They simply traverse the thing that you give them, and if you want, they store each element of the thing you're traversing in a variable. So if you write for I in 1 through 10, what you're doing is iterating over a range 1 through 10, and for each value in that range, I will be assigned to that value, and the loop body will be executed. On this slide, I also use a cleaner syntax for single line for loops, which uses a do keyword. Chapel is not indentation sensitive, so normally you'd need to surround your code using curly braces to specify the part that should go within the loop body. However, if your loop only has one statement and you don't want to create a whole bunch of curly braces for that, you can use do. And that completes my introduction to the various language features, and we have a working implementation of one-dimensional heat diffusion. But does this implementation really make the most out of a modern computer? It doesn't. And the reason is that, like Michael talked about, parallelism is very important in modern computing. And this implementation does not make use of parallelism. modern CPUs have, modern CPUs have more than one processor core, and as a result, can do a lot of work in parallel. To fully leverage all of these cores, and therefore speed up our computation, we need to use all the cores together. And so, how can we make Chapel's features help us with that goal? I'll talk about this in the next part of this presentation. Alright, in this part of the presentation, I'll be using parallelism and Chapel's support for it to improve the performance of our program. Let's take a look at our problem and the stencil that we used to compute it once again. As you can see here, to compute the temperature value at the next time step at index I, all we need are the values of the neighbors of I and I itself in the previous time step array, in this case UN. This means that to compute the temperature at a different index for this time step, we can once again refer to UN and not worry at all about the value at U sub I. So what I'm trying to say is that every value in U can be computed independently of every other value in U. And this means that we can perform our computations in parallel. Chapel has nice support for this in the form of for all loops. So here on line 8, I replaced the for loop with a for all, turning the loop body or turning the loop into a parallel loop that will make use of every CPU core available to the Chapel program. This means that the loop body on lines 9 and 10 will be executed in parallel on as many processors as possible, and therefore our program becomes a parallel program. The rest of the code is completely unchanged. All I had to do was change one keyword, for to a for all, and we got parallelism. Chapel's for all loops are very powerful, and we'll be seeing a lot of them in the future, and they are a quick and high-level way to get data parallelism. So, having made our program parallel, I'll now hand this over to Jade to look at the performance characteristics of the serial and parallel programs.
So now that we've tested the problem and we've looked at it and run it, let's actually compare the performance of the serial version to the parallel version. And to do that, we're going to leave this code space for this example, as code spaces are pretty resource constrained, and we want to look at what a real machine can do. So we're going to switch to my development machine, which has 8 processor cores that it's going to be able to use. So we'll go ahead and compile the first version, the serial version, and making sure to use -- fast. And we'll also go ahead and try out the parallel version, again compiling with -- fast. And if you recall, we were able to run the serial version with various problem sizes like 1,000 and 10,000. We're going to start by running with 1,000,000, and we'll run the serial version with that and see what kind of performance we get. So it's taking about 2 seconds versus I'm going to go ahead and run the parallel version again with 1,000,000. And you see it's taking about 1 second. So we've about halved our time, and of course we can do this same experiment with a slightly bigger problem. I'll just increase this by a factor of 5. And that takes about 10.5 seconds, and we'll increase the parallel version by a factor of 5. And that again takes about half the time. So go ahead and try this out and compare the performance between the serial and the parallel versions. Keep in mind that a code space is not going to give true performance results, as it only has limited resources that are running virtualized. But go ahead and try this out.
All right, so now I've shown you how to change the for loop to a for all to make use of data parallelism, and Jade has explored the performance implication of this, hopefully proving to you that for all loops making use of parallelism result in a performance improvement. And now I'd like to talk about for all loops in a bit more detail to understand how they work and how we can most effectively make use of them. The gist of what a for all loop is that it's basically like a for loop except parallel. When you write a loop like that on line 8, the way that the for all loop is turned into parallel execution is determined by what is being iterated over. So in this case, omega hat is what determines the parallel distribution strategy that the for all loop should use. The iterand is used to specify the number of tasks, which are assigned to CPU cores and therefore executed in parallel, as well as which of these tasks will run which iterations of the loop. In practice, the iterands of the loop will determine the number of tasks and cores that is appropriate for the current hardware. So if you have 4 cores, this will likely figure out how to split the work across those 4 cores evenly. In essence, though, the for all loop executes the parallel iterator of the iterand. And most things in Chapel have parallel iterators. This includes arrays, domains, and ranges. So data structures in Chapel know how to be traversed in parallel, and the for all loop makes use of that. And when you use a for all loop, you're actually opting in and asserting several things. The first thing is that your loop should be able to be executed in parallel. That means that if 2 loop bodies, like the one on lines 9 and 10, are executed at exactly the same time, that's not a problem. This property is not true for all possible loops, so you should not make every loop into a for all. For instance, we have a non-parallel safe loop on line 6. It doesn't make sense to try to simulate multiple time steps at the same time because there's a dependence between them. So you might end up swapping arrays haphazardly or doing very odd things if multiple tasks were writing to the same data, trying to race for some kind of computational answer. Another property that you assert when opting into a for all loop is order independence. And that means that the various iterations of your loop can be executed in any order. For instance, you might execute, if you were iterating over the range 1 through 6, the loop body might be executed with I being equal to 1, then 2, then 3, and so on and so forth. Or it might be executed with I starting at 6 and then going all the way down to 1. Or any combination of the above. And the reason for this, or one possible reason for this, might be that each loop body was sent to a different CPU or a different CPU core, and that particular CPU core got to the loop body faster than any of the other CPU cores, which is possible. So you should be prepared that your iterations can happen in absolutely any order. And once again, this is not true for all loops. On line 6, the loop we have cannot be executed in any order because we are simulating the transfer of heat as time goes forward. So we can't simulate the last step in our sequence before simulating all the ones before it. So there's order dependence in the loop. And finally, you're asserting serializability. So although I talked about many loop bodies executing in parallel and executing out of order, it's entirely possible for the for all loop to be executed in the same way that a for loop is executed. This might be because the loop body or the iterand is too small, so if omega hat was only 3 elements, it might not make sense to distribute it across multiple cores. And there can be other heuristic reasons for why that might happen. So you should not expect that your loop body will create a certain number of tasks, because that is not a given. So for instance, if you were hoping for one task to create a lock and then another task to unlock it, you might end up in a situation where your loop never finishes executing because it's deadlocked. While on this topic, I'd like to talk about data races. So, like I mentioned earlier, for all loops assert order independence, which means that in our particular code, writes to the array U can happen in any order. Like I mentioned earlier, omega hat can be iterated forwards, backwards, or in all sorts of pieces, and of course all these iterations can happen in parallel. the code that we wrote is safe because every iteration of the for all loop actually writes to a different index of u. So it doesn't matter if I write to u0 or u1 first, because the writes will be independent of each other. However, if I change this code to all write to a single index of u, then what I end up with is a data race. So in this case, if I iterated omega hat in order of increasing numbers, then the value in u1 will be that of the very last stencil computation, or the rightmost stencil computation. Whereas if omega hat executed backwards, the value in u1 will be of the leftmost stencil computation. And because of this, we effectively say that various tasks are racing to write to u. Chapel allows data races because, in general, being able to share resources in a parallel environment is useful for certain classes of parallel problems. However, if you'd like to synchronize your data and avoid data races, Chapel also provides features such as atomic and sync types and barriers, which can be used to ensure that things execute in a particular order. We won't be covering them in this tutorial, but you should know that they're out there. Okay, so now we've looked in quite a bit of depth into a parallel implementation of heat diffusion that makes use of all CPU cores. But even having this in our hands, we might want to try push more performance out of it. And we could do this by leveraging different types of hardware that we might have available. One type of hardware is GPUs, which are becoming increasingly common in both personal computers and high-scale supercomputers. GPUs excel at certain forms of parallel programming, and for those forms of parallel programming, if you use GPUs, you can get a significant speed up. So if you have a desktop or even a supercomputer that has both CPUs and GPUs, you might want to make use of both. An alternative approach to getting more performance out of your hardware is to connect multiple computers together. This boils down to dividing and conquering the work. If you have one computer that can complete a simulation quite fast, could you use 20 computers to make the work go 20 times faster? For certain problems, this is possible. Also, some problems can be so big that you just can't fit them in a single computer's memory. And breaking it up across multiple computers can help you alleviate the challenges of that size. Chapel supports both GPU and multi-node programming, which means that you can push your hardware to even to get even better performance. And the way that Chapel supports both GPU and multi-node programming is using a single shared concept called locales. I will talk about locales next. All right, so what is a locale? The notion is a little abstract, but in Chapel, a locale is a compute resource that has several things available to it. The first is processors, which means that a locale can execute code. And the second is memory, which means that it can store variables. So a locale might be able to run code, such as our numerical simulation, and it should be able to store the variables that we declare, such as the array u, omega, and so on and so forth, into its memory. For now, it's easiest to think of a locale as either a compute node or a GPU. In the context of programming on your laptop or desktop, your device counts as a single compute node, and a GPU is quite literally a graphics card plugged into your computer or machine. So far, all the code we've executed was only on one locale. However, to push our execution to GPUs or multi-node systems, we need to branch out beyond that. But first, why do we need locales? Let's talk about a few concerns in scalable parallel computing that help motivate the existence of locales. The first concern is parallelism, which means which tasks or which code is running simultaneously on a particular bit of hardware. We started with a program that was not parallel, and only a single core was executing a single piece of code in sequence, serially. However, by switching to a for-all loop, we then made our execution occur on multiple processor cores. But all of that was happening within one locale, or one compute node. The next concern of scalable parallel computing is where code should be executing. If you have multiple compute resources that can execute code, then it starts to matter which one of them is actually doing so. Here in the picture, locale 0 is the only node executing any code, whereas locale 1, 2, and 3 are effectively idling. What we might want to do is have each locale run a part of the code, or some code, themselves. This way we've distributed our computation across multiple nodes. If the locales were GPUs, we would be breaking up our computation across multiple GPUs. And of course, ideally, we would also like to execute on every available core of every locale. This means that we'd be making the most use out of the computing resources that we have available. A related concern to where code should be run is where data should be allocated. For instance, I might have an array declared only on locale 0 and stored in locale 0's memory. However, if multiple locales are running code, then it might make sense to split pieces of this array such that each locale has its own piece that it's operating on. Or maybe it helps to copy the array completely so that every locale has its own private copy. When working with locale, Chapel provides several built-in variables. The most important one is locales, which is the array of locales available to the Chapel program. This array has as many entries as there are numbers of available locales, represented by the numLocales variable. For each locale, we can ask questions about its properties. For instance, we can ask how much physical memory is available on a particular node, what the masked task parallelism value is, which is effectively just how many parallel things we can be doing at the same time. And we can also ask for a unique ID and a name for that locale. Okay, so I've shown you pictures of locales and I've told you about some variables, but now it's time to look at a piece of Chapel code that actually makes use of these features. And now I'll walk through this piece of code while showing you visually how execution is being transferred. When we launch a Chapel program, it starts on locale 0, and it starts only on a single CPU core of that locale. So in my picture, the gear is only spinning in one blue square on locale 0. If we were to declare an array such as var a, that array would be declared in the memory of the locale on which code is currently being executed. Since we're currently running on locale 0, that means a is stored in locale 0's memory. I can then use what's called an on statement to transfer the execution of my code to a different locale. Here, I'm accessing index 1 in the locales array, which is the first locale as opposed to the 0th locale, and feeding it to the on clause. The code inside the on clause will be executed on locale 1. In my photo, this is represented by the gear spinning in a blue square on locale 1. Now, if I were to declare another array, var b, this array would be allocated in the memory of locale 1, since that's where execution is taking place. If I needed to access the memory from locale a, for instance, to assign twice the values in a to the array b, Chapel will automatically perform memory access to locale 0. This is modeled by the yellow arrow in my diagram. Once you reach the end of the on block, execution returns to the locale on which it previously was. So once the on clause is done, we're back on locale 0. Variables that were declared in that block go out of scope and therefore are deallocated. So the variable b is no longer in locale 1's memory. So what I've shown you so far is a distributed computation because we've transferred execution among multiple available locales. However, it's serial. We're only ever doing one thing at a time. Now let's look at the examples we've seen so far through the lens of locales. The very first program, the one that we started with, only executes on a single core of locale 0. This is a serial and local computation, where local is the opposite of distributed. You can see this by the gear spinning only in one blue square of locale 0. When we switched to a for all loop, we made use of multiple CPU cores of our locale. So although we were still executing locally, we were now in a parallel execution mode. However, so far, both the for and the for all loops left us on only a single locale, whereas all my prior pictures showed multiple locales. So how do we use these on statements that I've shown you to build on the programs that we've seen so far and make our code support GPUs and multi-node systems? I'll talk about that in the next section. In this section, I'll be talking about improving performance by using multiple locales. The thing with GPUs is that unlike general attached additional nodes, they are a physical part of the system to which they're connected. Because of this, we don't model them as just locales, but rather as sublocales of a different locale. Notionally, any given compute node modeled by a locale has connected to it, and within it, sublocales that represent the GPUs that it has available to it. In this case, we have 4 locales, and each of them has 4 sublocales, each representing a GPU. Because GPU cores are quite different from CPU cores, I'm using an orange or yellowish square to represent them. Let's walk through a Chapel program that uses Chapel's GPU support and watch how execution transfers between these various locales. Like I mentioned before, when you start a Chapel program, execution begins on a single core of locale 0, and here is no different. When I write var x equals 10, that's being executed by the first core of locale 0. Then I use an on clause to transfer to a GPU. In this case, here is a variable that represents the current locale, and GPUs is a field of the current locale that is an array of GPU sublocales. There is one GPU sublocale for each available GPU. I index 0 into this array to get the first GPU available and transfer execution to there. Once on the GPU locale, I can use a variable declaration to create an array within the GPU's memory. Then, a for all loop, the same kind that we've seen in prior parts of this presentation, can be used to execute code in parallel on every GPU core within the GPU. You can see this by the various tiny gears spinning in the orange squares on GPU 0. Once execution exits the on block, as before, the variable a goes out of scope and is deallocated, and execution returns to the locale on which it was prior to the on statement. In this case, since we started on locale 0, we are back to locale 0, and there we write a len x. To transform our program into a GPU-enabled program, it turns out to be sufficient to wrap the for all version in an on here.gpus block. If we do this, we tell it to execute parallel loops on the GPU when possible, and because our loop is GPU eligible, it becomes a GPU program. So here we have a parallel program, and it performs as many GPU kernel launches as there are time steps, because within each of these time steps, numbered 1 through n, we have a for all loop. If you're not familiar, a GPU kernel launch is effectively what happens when you execute a program on the GPU. Okay, so now we've not only made a parallel program, but also transferred execution between locales to target a GPU. However, at any given point, we're still only executing at a single locale. How can we make use of multiple locales at the same time to divide and conquer our heat diffusion problem? To talk about that, we need to look at another aspect of the Chapel language that I have previously glossed over: domains. I mentioned before that domains are first class or are index sets. In short, they represent the indices that a particular array can have. On line 3, we declared var u, our array u, to have the indices governed by omega, which meant we can use numbers 0 through nx to index into u. Domains are more than just index sets. They are a fundamental concept in Chapel for data parallelism. I have some examples on this slide of other domains that we might be encountering beyond omega and omega hat. For instance, const D is a two-dimensional domain that is 4 by 8. In this case, m is 4 and n is 8. And the expand call, which we've seen before, simply shaves off, when a negative number is provided, shaves off one step from the domain's edges. So expand -1 will give us a 3 or a 2 by 6 domain. I have a picture here of this. So D, as I said, is a 4 by 8 domain representing the various indices that can be used in some array. And inner represents the region of this domain D that is one away from the edge. Domains can be used to declare various arrays that have certain indices available to them. So in this case, if I write var A, B, and C and have them all use domain D, I'll be creating 3 4 by 8 arrays, each of them containing real numbers. In the particular case of this program, omega is a one-dimensional domain, and omega hat is simply omega but with the boundaries omitted. When we create U, U has the domain omega, and as a result has the indices that correspond to the elements of omega. When we create UN, we copy the domain of U, and as a result we end up with 2 arrays, both of them over omega. As I mentioned earlier, we use omega hat to avoid out-of-bounds accesses in our stencil computation. Now let's talk about what we'd like to happen when we distribute the computation for our stencil across multiple locales. It seems like the easiest way to do so is simply to cut up a particular input array and perform the stencil computation on each piece of this array on a different locale. So here I've used the 3 red dotted arrows to represent the divisions of the arrays U and UN across locales. Each locale can then perform the stencil computations in parallel and independently of all the other locales. Since all 4 locales are performing the stencil computation at the same time, I represented this as 4 gray arrows, 1 per locale. Of course, each locale can also be executing the computation in parallel on its CPU cores, so there might be more than 1 arrow on each locale. If we do this, we take advantage of all the memory and compute resources of every locale that we have available to us. It turns out that to do this, all we have to do is change our previous definition of omega to one that uses Chappell's block distribution. A block distribution does exactly what we can see on the screen. It divides a given domain into equal portions, assigning each portion to a particular locale. Thus, when we make the change and create a block distributed omega on line 2, and keep the for all loop from our parallel version of the program, we end up with a program that uses every CPU core on every locale that we have available to us. Note that we only had to do this once. Omega hat, because it's created from omega, inherits the distribution of omega. Similarly, because var u and var un are declared using omega, or rather u is declared using omega and un is declared using u, they're all distributed in the same way across many locales. Let's talk a little bit more about how this works. Well, we created a block distributed domain, and as you saw earlier, block distributing a domain simply means cutting it up into pieces where each piece is mapped to a particular locale. Like I mentioned earlier, omega hat inherits that distribution because it's created from omega. Similarly, u and un eventually inherit that distribution as well. Then, when we use the for all loop to iterate over omega hat, the for all loop invokes the parallel iterator of omega hat. Because omega hat is block distributed, this for all loop will know to transfer execution to several locales, and therefore make our program distributed. When we access values that are out of bounds on a particular locale, Chappell automatically performs communication to access that data from a different place. Domain distributions are a very powerful feature of Chappell, and they are effectively recipes that tell it how to break apart arrays and even iterations into pieces. In effect, we can take a particular computation at the top level and map it to the various locales and processors that we have available to us. When we use a domain distribution like we did with block dist, we specify several things. First, we specify how various indices in the domain are associated to locales. In this case, we allocated a fourth of the indices to locale 0, and then we mapped the next fourth of the indices to locale 1, and so on and so forth. We also can use the domain distributions to specify how arrays and domains are laid out in memory. For instance, we can control whether an array is in row major or column major order, or we can maybe use sparse arrays to reduce memory when possible. As we saw with the for all loop, distributions also specify how for all loops should iterate over the data. So the domain distribution can be used to instruct Chapel how to traverse the data and how to map the computation to various locales. And there's also a few other things that domain distributions can specify. Excuse my premature slide transition. I have a couple more visualizations of two important distributions in Chapel. The first, as I mentioned before, is block dist. In general, this distribution divides a domain evenly across several locales. Here, I have a two-dimensional domain, D, the one that we saw before, and I'm dividing it across what looks like 8 locales. As a result, we have these neat little colored squares where each different color represents a different locale. Another common distribution is cyclic distribution. This one assigns one element of the array to one locale, the next to the next locale, and so on and so forth. When it runs out of locales, it wraps around, forming a cycle. Having seen serial, parallel, GPU-enabled, and distributed versions of a heat diffusion simulation, we can now move on and look at a two-dimensional version of the same problem. The two-dimensional version is more interesting because it has some practical considerations when making it parallel and distributed. Like the one-dimensional version, the two-dimensional version is governed by a differential equation. And once again, you don't have to understand the differential equation to understand how this tutorial will solve the problem. Suffice to say that there is also a discrete version of the differential equation above that we will use to directly simulate the flow of heat through our plane. In the pictures at the bottom left, you can see what we'll be simulating. A particularly hot square within an otherwise cool region will be gradually transferring its heat and getting more and more diffused through the material as time goes from time step 0 to time step big N. In fact, the code for this simulation is very, very similar to the one-dimensional case, with about 3 notable changes. The first notable change is that we've changed omega to use 2 dimensions. So here, in addition to the 0 through nx range, we also have a 0 through ny range. This makes omega a 2-dimensional domain, which we need because our problem is now 2-dimensional. Next, on line 4, I had to adjust the initial conditions to specify what region of U, which 2-dimensional region of U, I should say, was made hot, or hotter than the rest. And finally, on lines 9 through 12, I've changed the loop body to use the 2-dimensional discrete equation from the left side of the screen. Visually, when we perform this computation, it's easiest to see it like this. For a particular point in U, we need to access 5 points in the previous time steps array UN. Specifically, we need the point's previous temperature, as well as the temperatures of all its neighbors to the left, right, above, and below. This results in what's called a 5-point stencil. Once again, the temperature value at a particular index in U does not depend on any other value of U, only values from UN. Since UN stays constant, what we can do is perform this computation in parallel like we did with the one-dimensional version of the loop. Here, I'm once again showing the for loop as well as the loop body, which contains the parallel equation, not the parallel equation, the discrete equation approximating our differential equation. Specifically, you might notice that the I-1, I+1, J-1, J+1 are ways to offset the coordinates to access these left, right, up and down neighbors of the current point. We'll jump straight to a block distributed version of this computation by using the block distribution on omega. Here, we make a very similar change to the one we made in the one-dimensional case by using blockDis.createDomain and giving it two ranges, 0 through nx and 0 through ny. The definition of omega hat remains the same. Since we're using a block distributed domain omega when we have 4 locales, we'll end up cutting up our array into 4 quadrants, like I have in the bottom right of the slide here. Also, since we're using a block distributed omega, the for all loop will know to perform the computation across the locales that we have available to us. And each quadrant will be assigned to each locale if we had 4 locales. The picture would look a little different if we had a different number of locales, but I've chosen 4 here to make this clearest. As before, it's possible that to compute the value at a particular index, we need to have or to access a piece of UN that is outside of the current locale's chunk of the array. For instance, in the bottom left of the first quadrant, we're accessing the left neighbor of the point, which lies outside of that first quadrant's piece. Chapel will automatically perform communication in this case. However, communication tends to be pretty expensive, and in the case of performance analysis, it tends to contribute a fair bit to the execution time of a program. The reason for this is that communication has to go over network, and instead of accessing memory on the current node, we have to go through the network and talk to a different node, request information, get that information back over the network, and so on and so forth. As a result, Chapel provides a COM diagnostics module that helps track communication and thereby help you find and reduce the amount of communication that your program is doing to improve performance. The COM diagnostics module is currently unstable and its API is subject to change, but we find it very important, and so we'll show during this tutorial. The common pattern is the following. We use a use statement to bring all the symbols in COM diagnostics into scope. We then call a function called start COM diagnostics to begin tracking the communication that our program is doing. After that, we do whatever computation we wanted, which might incur communication. After that, we call stop COM diagnostics to click the stopwatch and stop tracking the communication that has occurred. After that, we can use print COM diagnostics table to show the amount of communication that was performed by each locale in our program. In this case, I have an example table if we had 4 locales. In this table, get represents the number of memory accesses that a locale did in which it retrieved information, and put represents the number of times that it tried to write information to a different locale's data. So here, locales 1, 2, and 3 performed 105 get accesses, and 5, 4, and 7 put accesses, or put calls, respectively. When using COM diagnostics, it's important to compile with the -- no cache remote flag. Chapel tries to cache communication to avoid it, but this can lead to unpredictable results when measuring communication counts. As a result, we recommend turning off that caching to get an accurate representation. Now, I'll hand it over to Michael for a hands-on that involves communication counts in our 2-dimensional block distributed version of the program.
Earlier, we saw an example where the value of a variable is transferred between locales, or in other words, where remote access can cause communication between locales. In this hands-on, we're simulating a bigger system with just one machine. The counts of the number of communication events generally won't change when moving to a cluster supercomputer, but the performance will. So you can measure the number of communication events on your laptop or a PC or even in the code space, and that will tell you information about how your application will perform when you run it on a cluster or a supercomputer. So go ahead and try these commands. Try these commands out and see what you can find about how increasing the problem size changes the number of communication events when we're using the block distribution in our heat diffusion application. Go ahead and pause the video and try that now. All right, let's try it out. Let's try it out together. So first thing we need to do is compile our heat diffusion code. With GasNet. I forgot to put the name of the compiler. Let's try that again. And then this flag, I forgot to put 2 dashes. Let's try again. By the way, another way to do this kind of compilation is to use a flag to ask for GasNet mode instead of the environment variable. I'll show that really quick here. Either way, we're compiling and we're going to run with many processes on the same machine. This is not a supercomputer cluster, so it's just one machine I'm running on. It's going to be simulating a distributed memory system. So let's try running it now. We'll run with 4 locales. That's like 4 nodes in our simulated machine. We'll ask for communication diagnostics output. I have not put the uppercase in. We'll try again. Okay, so you can see that there were about 25,000 gets from locale 0 to another locale. Let's bump up the problem size and see how that changes the number of gets. When we increase the problem size, the number of gets just about doubled. And that's what you can see in this picture here. This is just a picture version of the COM diagnostics table. So locale 0 had this many gets when run with a 256 by 256 problem size, and this larger number when run with the 512 by 512 problem size. You can see that the number of gets is approximately doubled as we quadrupled the problem size. So that would be an issue for this application scalability on a big system. I'll turn it over to Daniel to tell us about a way to solve this problem.
Thanks, Michael. The crux of our issue is that for every point along the boundary of every quadrant, we have to perform an individual communication event. For instance, if we look at the bottom left of the first quadrant, we need to access the values of the neighbors to the left and below that point, and we have to do so by communicating with a different locale. Since we do this for every point, we end up creating a large number of communication events, and the bigger the problem gets, the more communication events. To address this, we use what's called a stencil distribution. The stencil distribution helps create a buffer along the boundaries of our quadrant and store that buffer locally. As a result, when we perform communications for every given point, we access the buffer instead of performing network communication. And thus, we reduce the amount of communication overhead in our program. Of course, that buffer needs to be populated somehow. And to do this, we have to call the updateFluff method in our program. We do so right after we swap the arrays, and also right before the loop, because by the time we get to the loop, we already need to have the buffer ready to perform these to perform these accesses across boundaries. Visually, it looks something like this. For instance, suppose that we're the locale from the bottom right quadrant. Here, we know that we'll need to access at some point the values from the bottom of the upper right quadrant, the right side of the bottom left quadrant, and the corner of the top left quadrant. So what we do is we copy the values from those regions into a local buffer on our own locale. Then we can simply access those values instead of performing communication events. We call these yellow/orange values fluff, and updateFluff is what is the function that actually performs this copying. When we then perform these accesses, we avoid having to do communication and therefore we reduce the amount of communication events that our program performs. Of course, to actually make these copies, we do have to communicate, but we can transfer data in bulk, which helps save a lot of time. And now I'll hand it back over to Michael for another demonstration, this time including the block distribution and the stencil distribution.
All right, now that we've learned a little bit about the stencil distribution, let's see how we can use that to address the problem we saw in our earlier hands-on. Go ahead and try these commands to see how the number of gets changes when you use the stencil distribution instead of the block distribution. Go ahead and pause the video and try this now. All right, let's do it. Let's look at it together. So I'm going to just pop over to the window where we were using where we were running our commands, and I'm going to compile. I have spelled GasNet wrong. Let's fix that. I'm going to compile this stencil version. And you can see I have run from last time, I have the communication counts table from running on the block distribution here. So to compare, we only need to run it with the stencil distribution. So you can see that there are significantly fewer communication events from each of these locales. We can even try running on a bigger size. Let's try 700. And you can see that the number of communication events stayed stable even as our problem size increased. So that's why the stencil distribution helps with the performance of applications that are working with this kind of stencil communication pattern, because it can minimize these communication events and it can make them be limited even as you're increasing the problem size and the amount of data that might need to be communicated. I'll turn it over to Daniel.
Thanks, Michael. And with that, we've reached the end of this tutorial. If there's anything that you take away from this, I'd like it to be the stuff that's on this slide. What we've done is used direct simulation of a heat diffusion problem to introduce parallel computing in Chapel. We've seen that parallel computing is key to getting good performance on modern hardware. Chapel specifically has powerful language features that make parallel computing more user-friendly. Chapel's for all loops make it easy to turn serial programs into parallel ones and make use of data parallelism. And those same loops can even be used for distributed execution. Chapel's on statements can be used for granular control over where code is being executed, including a different computation node or a GPU. And distributed domains and arrays make it easy to use storage across many locales. Of course, Chapel supports parallelism across a whole spectrum of hardware, starting with personal laptops, workstations, including ones that have GPUs, and working our way up all the way to supercomputers. You can see the link on this slide, which will also be in the video description, to get the source code of the programs in this tutorial, as well as a README file that points you to various resources if you want to learn more about Chapel. Thanks for watching.